accelerated gradient descent. Basically, you do something called extrapolation. There are two extrapolation schemes. One is called heavy ball method, and another one is Nesterov acceleration. The idea of this kind of method is to add something called momentum. Momentum means previous history. Say I'm considering heavy ball method, HBM. Previously, you know that the update is a gradient update. That means you move the point along the negative gradient. So let's denote that point X updated. You have extrapolation, you add momentum. That means you do this. So what is momentum? It's previous history. So what is this thing? So let's say this xk plus 1 is here. This xk is here because of the gradient update. So this minus this is basically this arrow. And let's say this updated is this point, that means here. So from this step, this is gradient update from k to k plus 1. But now you add the momentum along this direction. That means you push this point here by star amount. What is star amount? Basically, it's the norm of this thing.
I have a question. What guarantees us that this new direction, which is the previous direction, goes in the right direction?
Good question. Theoretically speaking, you can make sure this direction go to the right direction by doing some restriction. Suppose you know that at this point, the descent direction, that means the set of direction you make the function value decrease, let's say is a cone along this direction. Let's say, then if you want to make sure this push will decrease the function value, you should make sure the pushing direction is within this cone. But in practice, actually, you cannot make sure this is always within the descent cone direction because you don't know. But in practice, you don't care because actually this will magically make things very fast, even though this is not pushing the point to decrease the function value. In the very beginning, I'm saying that an iterative solver is trying to produce a point x1, x2 such that this is true. Now I'm telling you, by doing extrapolation, this is no longer true. For some k, maybe this is bigger than this. That is possible. But by doing the extrapolation, the overall global behavior of this will go down very fast. That is, you go up in some iteration, but then you go down much more in the future iteration. So this is the magic. And actually, Nesterov saying that by doing this, we don't have the decrease of all iteration, and actually that gives the freedom, making the decrease of the function value faster. Now let's look at the physical meaning of the update. So this is gradient descent, normal gradient descent, you don't do anything. So basically the meaning is you move x in direction this for this amount. HPM, heavy ball method, you have this new thing. It's like you do gradient descent, then you move the updated x. This is the updated x in direction. This is the direction for this amount. So if your solution point converge, xk and xk minus 1 is the same, then this point disappears. And also gradient is 0, so you don't move. So this is okay. And lastly, about Nesterov acceleration, okay, you suddenly see the sentence become so long and so colorful because this is quite complicated. So this is gradient descent with momentum. This is like adding momentum after you perform the gradient descent. What is Nesterov acceleration? You do the momentum before the gradient step. And after you do the gradient step, you push it on the momentum. So this is the Nesterov acceleration. You can read it by yourself. Let's look at the algorithm. Basically, it's the same. So previously, without the blue color, is the gradient algorithm. Now with the HBM, I just have the new thing in blue. The new thing is you in the initialization, you need to guess this value. And if you pick beta is 0, then this disappears, then you just reduce to gradient descent. This is an illustration. Red is a normal gradient. Blue is HBM with a fixed beta. And I only show the 4 iterations. So for this example, you can see red and blue go to the solution point in one step is the same. But if you look at this one, this is more elliptic. For the red one, it's the normal gradient. You can see it zigzag. But for the blue one, compared to the red one, it zigzag less more along this line. So that's why the blue one go to the solution point faster than the red one. And this is for beta equal to 0.1, and this is for beta equal to 0.3. You can see they both work. And then now with Lipschitz constant step size, you see something similar. Here is a very important message. If f is nice, gradient descent don't need acceleration. And you need to repeat this sentence 3 times because this is so important. Just don't do acceleration blindly. If you do it blindly for any problem, that means you don't understand why you need acceleration. Now let's consider different beta, let's say 0.1 and 0.3. And now I plot the value of the point. And then you see for 0.1 beta, the red one is the unaccelerated gradient descent. This is normal GD. It's moving like this. For the blue one, you see it's moving like this. And you see something. Actually, this line have a different slope than this line. And also, this drop faster than the red one. For this case, the blue line actually sometimes go over the red one. That means for this case, beta equal to 0.3 actually is not good. You may wonder, is it the smaller beta, the better HBM? The answer is no. So let's say this is the red line, is gradient descent. Now you pick it 0.1, so it go down like this. Wow, very good. So what about 10 times smaller? Is the yellow one. Wow, much better. Then you may think, what about even smaller? Is the black one. And in this case, the black one is actually slower than yellow. So that means actually there is a value called best beta, and you want to find the best beta. For HBM, actually, you don't know what is the best beta because here I'm just guessing the value of beta. So it comes to the Nesterov acceleration. Let's review. This is gradient descent. This is HBM. Nesterov is you do the momentum term before the gradient descent and then you add it back. And actually you can split this whole line into 2 lines. This Nesterov and Nesterov 2 are the same thing. And then we just saw that HBM with a fixed beta, and actually there's a best beta. And here comes the magic. Nesterov give an update scheme for beta. If you pick alpha 1 between 0 and 1 and then update beta following this crazy formula, then it works. And in fact, this is really magic. Why this works, nobody know. Even up to now, nobody know. So you have to take it as granted. And in fact, this can be proved. It really works. That means it really converges faster. But why? It's still a mystery. And we will try to understand this by some other method. So what is Nesterov gradient? Before that, you only have the black thing that is for the gradient descent. Now, with the Nesterov acceleration, you have the blue thing. That is, you need to find a new parameter, and then you update like this, and then you do it like that. Let's talk about how to deal with more difficult problem. That is, now you have constraint. With the constraint set C, then you need to make sure the initial solution point inside C. After that, you update the gradient by project it onto C. This thing is basically, you have a Y. This Y comes from the gradient update. And then after you do the update, this Y, if this is outside the set C, then you move it back into the set. And if this Y is inside the set C, then you do nothing. So this is projection. And these 3 lines can be written in 1 line. So let's look at a simple set C that is just positive cone. That is, everything you have to be positive. Then the projection is very simple. It's just max it with 0. Now I denote this thing as this symbol. For the problem P, this P now I have this constraint. The whole algorithm stays the same, except that I have a projection after I do the gradient step. This is a very small change, but in fact, the whole sequence will still converge. This is the Nesterov acceleration. The only thing you change is only at this gradient step. This is the gradient step. That means you push the point along the negative gradient, and this is the update. So you only do this projection on this point to get the Y. You do not do the projection on this line. It is possible these xk are not in the Rn plus. Well, in this case, you just take yk as the solution point. For the unconstrained problem, that means you don't have this. you can take y or x as your solution, but now for this with the constraint, you can only take one of them. You can say you take this guy. Now I consider the NNLS non-negative least square problem on 50 by 50. That is, the matrix A is 50 by 50. Same, I just set the solution point as a zero vector, and then I initialize x0 by random in Rn, and let's say I pick alpha 1, this parameter as 0.9. So this is the curve. This free figure is the same thing, but I just zoom in different axis value. So for the curve, the red one is projected gradient descent with constant t. That means I use a Lipschitz step size. For the blue one is exact line search. You can see here for this plot, the red and the blue one actually looks exactly the same. And then you look at the accelerated projected gradient, you can see that the conversion is much better than the unaccelerated method. And you observe something. This line, the slope is like this. This line, the slope is like this. The slope is different actually tells you something. That is, the slope tells you the conversion rate. And furthermore, for the red and blue line, it's monotonic. It means every point is smaller than the point before. But for the accelerated method, you see at some point it goes up. This is the instant when the beta xk plus 1 minus xk is actually pushing the point to somewhere higher in the level set. But it does not hurt because you can see the global behavior is going down much faster than this original method. So as I told you, there's Nesterov scheme. That is, you do this crazy thing with beta, then it goes down so fast. Later on, he proposed another crazy scheme, another crazy equation. And then later on, somebody proposed this. This is actually called Fister coefficients. Now I'm telling you, you in practice, you can just use this, and then this will work. Theoretically, this is proven. This will also make the scheme go like this. And this is much easier to implement and remember than all this crazy parameter. And the only difference between all this scheme is just the little difference in the convergence. That is this kind of curve will have different speed going down, but globally speaking, they go down much faster than this. So this is the method, and there are also other ways. For example, let's say for the problem P, you can have this specific beta, and that's not important. In practice, I recommend you just do this. This is easy to do.
Why does Mr. Nesterov invent this kind of scheme when it doesn't really make the method better?
Okay, this thing is in this time, and Nesterov work now become very, very famous in the, let's say, last 20 years, last 10 years, because it is found very useful in large-scale optimization. This one actually is from year 2000. So actually this is 20 years after this. But why he make so many methods, I don't know. Maybe for fun, I don't know. In fact, the message is you can make use of this method, but I will say for practical purpose, you just stick with this. This is easy. And now I'm showing you why they work. This is the curve. This is the NNLS 100. Now this is the gradient descent without acceleration with constant t, that means constant step size. This free color curve is just basically accelerated projected gradient with different parameters. This is a more fine-tuned for beta. This is a very rough beta. And actually, Polyak studied this kind of thing, and he showed that there is a rule. As long as the beta fulfill the rule, then you can tune it whatever as you like. And that's the reason why he just tuned it like this, because this satisfies the rule. But the rule is not very important. The message is you just pick this, is okay. Adaptive restart. First look at the observation. This thing is called Nesterov ripple. That is, it goes down and then go up and then goes down and then go up. And you see this pattern repeat itself. And furthermore, you see this pattern is periodic. At this point, the point it go up is at iteration 12. And then at this point, the point it goes up is at iteration 25. And then the next one is 38. So what's the distance between here? 13. What's the distance between here? 13. What's the distance between here? 13. That means what? That means if we know when this point will goes up, we can do something called restart. So what is restart? Remember, in gradient descent, you always guess this. It's a greedy algorithm. Greedy algorithm means you always make improvement. That's why this is always making improvement. But for Nesterov method, you can go up. That means this is no longer true. Or in other words, Nestorov's method is not greedy. But here's the thing. You can do something like this. At this point, when you goes up, you abandon the acceleration. That is, go back to normal gradient when you see function will go up. That means here you run the gradient, then you will go down. Then here is the idea. At this point, you stop accelerate gradient for one iteration, and then after that, you restart the acceleration again. So this is called restart. Because accelerated gradient will go up, maybe you don't like it, then you stop at this point and go back to gradient, but gradient is slow, so you go back to gradient just one iteration after. Then you gain the advantage of both things. Go down monotonically and go down fast. Okay, this is the method gradient descent. Now this blue curve is the accelerated projected gradient. The green one is with restart. Because at the beginning, you can see move here, 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 here. At this point, the blue and the green are the same because the blue didn't go up. So the blue and the green are the same. But at this point, the blue go up. And for the green one, at this iteration, it run the gradient step instead of the acceleration step. And then in the next iteration, it runs the acceleration again, and then go down, go down, go down, go down. And this, now you can see the convergence. Wow. So this is just a very simple twist, and this makes gradient descent with acceleration even better. How to program it? So first of all, this is the APGD accelerator projected gradient descent using Nesterov parameter with no restart. With restart, you just add the blue thing. You just compute the error, and then you check. If the error goes up, then you do this again. That is, you go back to the gradient descent by updating this step, and then you reset all the parameters, because you start the algorithm for at k equal to 1 by this value, so you can restart the alpha k back to this initial value again. And this is the gradient step, and you put this yk back to xk. That means you move this yk as xk. So this is no restart. This is restart. You can see basically just a very minor change. And then this is using conditional number. Conditional number means you do this, and because this is constant, so when you do restart, you don't change because beta is the same for. So this is the comparison, and then this black method is the normal projected gradient, very slow. The thick blue is the Nesterov gradient, and then the thick green is the same, but you use Poisson parameter. You can see technically they have the same rate. All this method here have restart. I can say you just do this with restart is already very good. So this is the comparison of the scheme. The message is you just run acceleration for the problem if the function f is bad. Remember, if function f is good, you don't need acceleration. And then for running the acceleration, you just use the, for simplicity, you can use the Poisson parameter. It's almost as good as the best one, but it's easy to compute. And here's a warning. I always tell you restart is good, but actually maybe no. You can see for this method, the green one is mostly on top of the blue one. And this is a summary so far before the break. So we talk about this problem, talk about gradient descent. And then the thing is, f is bad. That means the level set is elliptic, then gradient descent is slow. To fix this problem, we use momentum acceleration, and there are so many momentum schemes. And the best scheme so far is Nesterov method, which looks like this. And to find a beta k, he gives this magic formula. And of course, you can use other easier formula. And to further improve it, you can consider restart.